Okay, hey, Chem 121 bonding students. I graded your quizzes, and it looks like we had a pretty good handle on the first page, where you did a calculation using a calorimetry equation. The back side of the quiz was a little bit more confusing, so I actually only graded the front side, because I think we still have a lot of misunderstandings about calorimetry and thermo calculations in general, so I thought I'd supplement lecture with a brief video overview of thermodynamics calculations. Sometimes it's good to take a step back and just say, what process should I use where? So hopefully you find this useful. If not, you can come and see me and get some additional help or go to the CRC. It's not a problem. Okay, so thermodynamics calculations come in, I guess when it really comes down to it, it's about 4 different flavors. Okay, so you have the theoretical and the experimental, and then they each branch off. For the level that we're doing it, which is still quite a bit, I don't think we have too much trouble with theoretical calculations. We just did those in lecture, and they come in 2 flavors. If you're asked to calculate the heat of a chemical reaction using the heats of formation, that's pretty straightforward. You go to those tables that I gave you, and you add up all of the heats of formation of the products, taking into account the stoichiometric coefficients, subtract from that the heats of formation of the reactants, taking into account, and I think that's pretty straightforward. Nobody has too much problem with that. And usually I would tell you, use the heats of formation to calculate the enthalpy of a reaction. And that's fine. Hess's law, it's kind of too broad for me to give you a summary here, but I think you get the idea, is you have a chemical equation you're trying to find the enthalpy for, and you're given 2 or more other chemical equations that you have to manipulate. You flip them, you cut the enthalpy in half because you have to change the code, and you add them, kind of like redox in a way. You're adding half reactions, sort of, to get the overall reaction. Then you add the separate enthalpies together. I think that was pretty straightforward. People didn't seem to have too much of a problem with that. But those are theoretical calculations. So heats of formation, Hess's law, and those of you in lab will see this in lab later in the semester. What I want to emphasize is the quiz. The quiz had 2 different kinds of calculations. They're both calorimetry, so they both start from the calorimetry equation. The heat of the system is the opposite heat of the surroundings. And we had a physical process on page 1. We had a chemical reaction, sort of. It was a dissolution, so it's sort of a chemical reaction on the back side, but we'll just call it a chemical reaction. Okay? How you set the equation up is very different. Okay? Well, slightly different, maybe not very different. But it all starts, system is surroundings. So on the front side of the quiz, we simply had a hot piece of metal, copper, being tossed into some water. So the system there was the copper metal. Fine, because that's what we're focusing on. The surroundings was water. So that's the basic equation. And you're asked, I think, it doesn't really matter what asked in the quiz, I think it was what's the initial temperature of the water? And you were given all the other data. So you put in your MC delta T's for everything. The mass of the copper, the specific heat capacity of the copper, which you're given, the change in temperature of the copper, which I believe you had the information. You had both the final temperature of the 2 combined and the initial temperature of a piece of copper coming out of a hot oven. You set that equal to the opposite, the negative sign has to be there, of the water, the specific heat capacity of the water, the change in temperature of the water, and the only thing you don't know, in this equation is the initial temperature of the water. The final temperature was given to you. So you set the equation up like this, put your MC delta T's on both sides because it's a physical process, and then you solve for whatever variable I ask. So this one was a little challenging because you had to do some more algebra. It wasn't just finding a specific heat capacity of a metal, but something that certainly most of you did very, very well. So that's good. For a chemical reaction, usually what you're being asked to do is to calculate the heat of that reaction. And I'm going to give you a heads up on the next test. I'm going to give you a calorimetry problem for a chemical reaction, and then give you the same calculation theoretically, and then ask you to compare the 2. So use theory to calculate the heat, use calorimetry to calculate the heat, and I set it up so the answers should somewhat agree with each other. So if you know what you're doing, it's self-checking. So you're welcome. All right. So for a chemical reaction, you're trying to usually find what is the heat of that reaction. So leave the Q. Leave Q system alone. That's your system, is your chemical reaction. And mostly these are going to take place in aqueous medium. So I'm not going to, take that too much into account. MC delta T. So this will be the change in temperature of the water or whatever medium the reaction is occurring in. We usually assume that the specific heat capacity of whatever solution you're mixing is equivalent to the heat capacity of water, so that stays constant. Two things to point out here. Units, units, units. Some people were using this number and then reporting their answer in calories. Doesn't make any sense, okay? That specific heat capacity is using joules. Also, delta T doesn't have to be in Kelvin. Some people were thrown by this. It's a delta T. So Kelvin or Celsius, so don't confuse the issue. Just subtract your two temperatures. Delta T in Kelvin is the same as delta T in Celsius. Okay. Some people were getting a delta T in Celsius, and then to the delta T we're adding 273. That doesn't make any sense. Okay. All right. Couple little variations here. Mass, you have to read the problem. If you're taking two containers and dumping them together, you have to add the mass of both. On the quiz, you had water and solid being thrown in there. You have to add the mass of the solid to the mass of the water, because that will be the mass of the final solution. Okay, so once you put in your data, don't touch that Q. You'll get Q reaction equals some number of joules. Oftentimes to turn that into an enthalpy, more traditional, kilojoules per mole, you convert that into kilojoules. I think everybody was okay with that. And then this is a very gross generalization. We would divide by the number of moles involved in the experiment. Now, I'm just being very general here. So in the quiz, just take your 12.5 grams of calcium chloride, convert it into moles. Divide your kilojoules, divided by the moles, and that will give you an enthalpy that you could then compare to, say, a theoretical calculation based on heats of formation. So I'm giving you an outline of one of the problems on the test. There'll be a calorimetry problem like this. You'll get kilojoules per mole. You'll do a similar calculation with heats of formation, and you'll compare the two. So a little long-winded there of a video supplement, but I hope that helps. Thank you.